is a little bit more complicated, but let's start out with the fundamental principle. And so what do we have to do in order to find the map estimator? What does the map estimator do? And it's actually in the name. Right, it maximizes the a posteriori distribution, which means we are basically trying to look at our fx conditioned on y, exactly, of x conditioned on y. And as usual, we want to write that in a sort of Bayesian form, because that's going to be easier to treat, right? We're saying it's y conditioned on x of y conditioned on x, fx of x. And this is what we want to determine. And now we say, well, our y is x plus w. Right? And W, we say, as per problem statement, is a Laplacian noise. So just for a change, we don't have it with a Gaussian noise. And so that means now that we can write our f of y conditioned on x as the fw of y minus x. And because now we're saying that in this model here, the x is treated as deterministic, right? Because we're conditioned on that. So therefore, we basically now have for our y conditioned on x the noise distribution, but shifted so that it's now centered on x. And so that is now lambda over 2 times e to the power of minus lambda magnitude of y minus x. And of course, we know that f of x, fx of x is single exponential. So this is mu times e to the power of minus mu x times the indicator function for x larger equal 0. So with that, we can now write our fx of x blah, 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 as f x conditioned on y, x conditioned on y. I'm rewriting this one more time, y conditioned on x, y conditioned on x, fx, as our mu lambda over 2 times e to the power of minus lambda mu minus x times e to the power of mu x, which becomes mu lambda over 2 times e to the power of minus lambda y, e to the power of lambda minus mu x. So this is our fundamental equation that we have to deal with. And if we are now furthermore assuming that if x is larger y and x larger equals 0, which of course is the only thing that makes sense since we have a single-sided exponential, and then we are saying that this fx conditioned on y, fy conditioned on x times fx of x becomes mu lambda over 2 times e to the power of lambda y to the minus lambda plus mu x. And this here was for the case that 0 smaller equal x smaller equal y. Right? Because in this case, the magnitude of y minus x is y minus x. And in this case, we have to flip the sign around. And so, sorry, I just see I missed the absolute sign here. And so this is our general equation, and these are now our two special cases. So really, if you got to the point where you said, this is the equation where we now have to find the maximum, or that we have to maximize, you've understood the principle of the map. Right? That's really the important thing here. Whatever follows afterwards is basically just numerics. Right? It's saying that how do we actually find the maxima over the various different cases. So this is our starting point for finding the maximum. Right? We have to do that case distinction. Essentially, all the difficulty just arises from the fact that we have a absolute value here in our exponent. So we then have to do the case distinction of, is this thing larger or smaller than 0? I mean, whatever is in the absolute value here. Right? And so based on that, we can then now just analyze, well, what are the different cases that we have to look at. So again, this here is for the case that x lies between 0 and y, and this is for the case that x is larger than y. And now we have to make the further case distinction of, is y larger or equal 0, or is it smaller 0? And x, of course, can only be larger than 0 because we said it's a single-sided exponential. But y, because we're adding a Laplacian noise to it, can be larger or smaller than 0. And so this is, again, a case distinction that we have to think of when we're doing that maximization. So if we're saying that y is larger or equal than 0, then we can just look at the two equations. Let's call them 1 and 2, the way that they are defined here. And we can furthermore see that at the point of x equal to y, they are agreeing with each other, and which we would hope is the case, right? Why should there be a discontinuity? Since, after all, the Laplacian noise doesn't have a discontinuity at 0 as well. So then we now have the function mu lambda over 2 e to the power of minus lambda mu times e to the power of lambda minus mu y is mu lambda over 2 e to the power of mu y. And now we have to consider the case if lambda is larger than mu, then for the situation of 0 smaller equal x smaller equal y, that factor e to the power of lambda minus mu increases with x. So we get a maximization at x equal y. And because, remember, then for the case of lambda smaller equal mu, then we have, of course, e to the power of lambda minus mu x is non-increasing. So we have a maximum at x equals 0 for the first expression. And the second expression is maximized at x equals 0. And so you just have to go one by one through the different expressions and through the different cases, and there is not, for the maximization, right? Normally you would take the derivative and set it to 0. But here is what we are calling Randmaxima, meaning you get the maximum value at the boundary of the range of the values that you consider. And so you just look at, well, do you have your maximum at 0 or do you have it at x equal y? And that just is a question of, well, first of all, are you dealing with a lambda minus mu larger or smaller than 0? And then, of course, you have to look individually at the different expressions and seeing for which ones is that, for which case do you get the maximum where? And for the case 2, since x is larger or equal to 0, then that automatically means that x always has to be larger than y. So we only will be dealing with the second expression here. And so, sorry, only dealing with this expression here. My apologies, I wrote this wrong here. And since that function is always monotonically decreasing as a function of x, right, we know automatically that we have maximum at x equals 0. And so if we now put this all together, we are getting the case that for lambda larger mu, our maximum a posteriori estimator is y for y larger equals 0, and 0 for y smaller 0. And for lambda smaller equal mu, it is 0 for all y. And that is our final answer. But again, don't let the difficulties of these various case distinctions in the derivation distract you from the fundamental principle that we are applying here. I think that's really the thing I mostly wanted to remember, that, well, we have a maximum a posteriori estimator, and how do we what are we actually doing with that? Well, we are maximizing the a posteriori probability, and that is written in this particular way here. And that's the thing you need to remember. The rest depends on what particular distributions you're inserting here for x and w. Okay, now before we go to today's material, I want to briefly address the second midterm. Right? As you've seen your individual results as well as the statistics, and it was published last night. So we had a strikingly similar result to the first midterm as far as statistics are concerned. Both mean and variance were fairly similar. Now, the mean being around the value that it was tells me that there is obviously still challenges in translating the theory that we are dealing with here and the examples that I gave into dealing with the examples that we have at the exam. And I did notice that the homework results, generally speaking, are better than the midterm results. And so I think this raises the question of why there is more of a difficulty of translating things into the solutions when the actual exam time comes. And now, this is something that would be very difficult to discuss here, sort of in a general circle, because I'm sure everybody who has difficulties will be hesitant to voice out loud what those difficulties are. But I would encourage you to email me or, of course, come to the office hours. But if you prefer even anonymous suggestions, right, feel free to email me from an unidentifiable Google email or something like that, just saying that, well, I have problems, this and this. Is there something we can do to help in the preparation of the finals? And I'm definitely trying to help you along here and doing what helps you to better digest the material, but I would need to know what the difficulties are. And given the enormous spread of the points that we had, there were people who had essentially perfect score, and there were people with very significant deficits in there. It is, of course, difficult to identify what's really the core here of the issues. But if I see a trend somewhere of saying that, well, this would help, I'm certainly willing to try that out. So that's just the general statement in terms of the midterms. In terms of who should be worried, I mean, you, of course, can consider the fact that the grading is essentially going to happen on the curve. And so you should probably be concerned or look less at what is your absolute point measure, but rather at where are you relative to the mean and the variance. Of course, if you are both in midterms 1 and midterm 2, 2 standard deviations below the mean, then that's probably a 3-alarm fire. And if you are somewhere around the mean or better than that, then obviously you are in a reasonably good position. I would not consider that as a sort of cushion to now say, well, I don't need to prepare for the finals, obviously, right? But you are clearly well positioned for the finals. But for everybody, essentially, I would say that, well, you should be encouraged to prepare well for the finals. Also keep in mind the finals actually count more than the midterms. If you remember it correctly from the syllabus, it was 25, 25, and 40. So you still have a significant amount of points that you can collect in the finals. Okay, that was just, as I said, the statistical evaluation of the midterms. Now let's go back to the scientific material, and we started last time with a discussion of entropy, which is essentially a measure for the average level of uncertainty of information that we have in the outcomes of a random variable. And that's how we defined it last time. And we said that for a discrete random variable, h of x is the sum over all possible x's, p of x times the logarithm of p of x. And for continuous variables, we said, well, it's actually called the differential entropy, and it's minus the integral over x, f of x, times the logarithm of f of x dx. Right. And we said that is a measure, basically, of how much information is contained in a random variable, and this can be translated to how many bits do I actually need to represent information in a particular source that has hidden information in it. Right? How much surprise is contained in that particular source, and therefore how many bits do I need to, for example, transmit in order to make sure that a receiver can get all the information that's hidden in that source. And then we said that this has obvious applications in so-called source coding, in file compression, and because that tells us really how much really is needed in order for a proper representation. So it gives you, when you're developing new source codes, for example, in particular when we're talking about lossless source codes, then it gives you a measure of how close are you to the theoretical optimum. There is a whole bunch, or a whole direction of research, source coding theory, that also deals with lossy coding, that actually gives you a trade-off between the amount of information that you are encoding, or the compression factor, and the distortion that you are creating by not retaining all the information that's in there. And that is, again, a very interesting area, obviously not anything that we can deal with here in greater detail. But if you're, for example, wondering of why does a CD, for those of you who still remember that, has data stream encoding of music with about 96 kilobits per second, and when you're streaming from Spotify, you get maybe 10 kilobits per second. Well, because there is a lossy encoding. And depending on the type of music, the distortion that you're getting with that might be acceptable or not acceptable. But in many types of music, this is just considered as okay, and you're getting the appropriate quality, which also, for example, if you ever wondered, well, why do some streaming companies charge more when they're offering lossless streaming? That's basically the use of the original CD information. There is no further lossy compression on top of that, which obviously means that you need more bandwidth, a larger service to send the whole thing out, and so on and so forth. And again, depends very much on the type of music, whether you say that is worth it to me or not. So with that, we leave the regular entropy, so to say, behind, and we're now turning to conditional entropy, mutual information, and cross entropy. And here it's getting really interesting. So let's first write down conditional entropy, just formally, that it is h of y conditioned on x, so the entropy of a random variable y conditioned on the random variable x, and which can be written as expectation of x of p of x, h of y conditioned on x taking on the value small x, and just the normal description of what do we have with conditioning, which can in turn be written as the sum over the x p of x, the sum over the y. And so here we're now just plugging in the formula for the entropy that we have up here. And so this is p of y conditioned on x, log of p of y conditioned on x, which you can now rewrite as the sum over the x and y of the joint probability of x and y. And this is essentially log total probability times the probability of y conditioned, log of y conditioned on x, which you can also write as the expectation over the x and y of the logarithm of p of y conditioned on x. So this is the conditional entropy. Now, the next quantity, which you will see in a second is very strongly related to the conditional entropy, is the mutual information I of xy. And the mutual information, we'll see in a second, plays a core role in communication, and it's also strongly related to the cross entropy, which is one of the essential quantities in machine learning. And so we will actually see that maximum likelihood estimator, Kullback difference, mutual information, cross entropy, things that look like they are from completely different areas of work, actually all come together or have a common origin and a common relation to each other. So let's start out by just defining what is actually the Colbert-Leibler divergence. Between two distributions, P and Q. It's just defined as the sum of the P of x times the logarithm of P of x divided by Q of x. And you can just look at this as a definition and saying that, well, this is a measure for the distance between two distributions, and we take it as is. Because it involves a logarithm, you can already imagine, well, there is a connection to entropy and mutual information and so on, but we will come to that later on. You can use the KL distance. I don't want to pronounce Colbert-Leibler 30 times in this lecture. It's a tongue twister. And so we just call it the KL divergence. And you can use that, for example, to describe how well does a theoretical assumed distribution, let's say a gamma distribution, fit an empirical distribution. And you could just say, well, I'm declaring my Q to be the empirical distribution, or I declare P to be the empirical distribution, and then I say, what is the divergence, the difference, essentially, from the theoretical distribution that I see. Right? And you would just say, well, if that KL distance is small, then I have a very good fit. If the KL distance is large, then I have a bad fit. That's a very simple interpretation here. But we will get, as I said, much more relationship to the mutual information in a second. So mutual information intuitively tells us how much does the knowledge of variable x tell us about the realization of variable y. And to be a little bit more formal, we can say y of xy is the distance between the joint probability of x and y and the product of the marginals. How does that fit to the picture of what does x tell us about y? Well, if x is independent of y, and therefore x tells us nothing about y, then the joint probability is just the product of the marginals. And so if these two things are in complete agreement, then we would say, well, there is zero mutual information between the two. So when we write this down now as an equation of what is mutual information, we're saying that it is essentially the KL distance between Px of xy, Pxy of xy, Pxy of xy, divided by our Q is now the product of the marginals, and where we're saying that we assume there is no information about each other. So if x and y actually have no information about each other, and therefore this Pxy factors, then we have here the logarithm of 1, which would be 0, and therefore the mutual information between them is 0. Right? And we can rewrite this further as, and this is now just basically manipulations to come to various alternative descriptions, and this is sum over the xy of Pxy. So here I've just pulled out the P of y and summed over the marginal essentially. So that doesn't change how x relates to y. And that can be written as Pxy of xy times the logarithm of Py of y, Px conditioned on y, Px conditioned on y. And just basically rewritten this term here as the via, well, what is the joint probability, right? It's Py of y multiplied with Px conditioned on y. Actually, we don't need that step here. So we can cancel that out here. So this gives us now the x and y of Pxy of xy times 1 times the logarithm of 1 over Px of x plus the double sum xy Pxy of xy times the logarithm of P of x conditioned on y. Right. So I'm just taking this term here, and of course the logarithm of a over b is logarithm of a minus logarithm of b, and the minus sign, logarithm of a plus b, right, because we're 1 over px of y here, and is the logarithm of a plus the logarithm of b, and that in turn we can rewrite as the sum of minus px of x times logarithm of px of x minus minus. And you'll see in a second why I'm writing this in such a weird way, because this is now the logarithm of P of xy. Because this is now, this first term here, you will recognize immediately as this is our entropy of x, and just by definition. And this is the entropy of x conditioned on y. And so mutual information between x and y is the entropy of x minus the entropy of x conditioned on y. So if we do a little Venn diagram, and we can say this could be our entropy h of x. This is entropy h of y. This overlap area here is our mutual information. Right? This is I of xy. And now this dotted area here is h of x conditioned on y. Right? And that area here is h of y conditioned on x. So whenever you are doing a conditioning, you're reducing the entropy. And how can we interpret that? Well, if remember that entropy is the amount of surprise that we're getting from a source. Right? So if we know something already about that source, we're reducing the amount of surprise. And since sports analogies are very much en vogue, and if you are thinking about a general, I think it's football, right? A football game, you would say, well, who's the winner, who's the loser is a surprise. If you know one of the teams is the New York Mets, and then it turns out the New York Mets are the losers, there's not much of a surprise there. And so whenever you're doing a conditioning on information you're getting on the side, then that reduces the amount of surprise that you see. And so the more mutual information you have, the more that y already tells you about x, the less surprise do you have, meaning in your conditional entropy, about what you are getting from the source x. So let's just write that down. So remember, conditioning reduces entropy. And on a side note, we know that mutual information xy is larger or equal 0. And you cannot have a negative mutual information, because if you make that mental gymnastics and say that, well, if I know about x, then I know y is, or if I know y, then I know x is doing something negative, or the opposite of what you would normally expect. That's still information. Right? If you always know the opposite is true, then that's just the same as if you always know the normal thing, so to say, being true. So there can be no such thing as negative information. You can only have zero information, which you get exactly if x and y are independent of each other, meaning that the outcome of y doesn't tell you anything about the outcome of x, and vice versa. Now, very strongly related to this topic is the cross entropy. And I'm writing this now out of memory because I seem to have lost the preparation sheet that I had for this. But the cross entropy is the sum of the pxy times the logarithm of the p of x. Or if you want to go back to the Kullback-Leibler divergence, and you can actually say, well, it's the p of x times the logarithm of 1 over q of x. And so it's basically just, which you can also express as the expectation of over p of the logarithm of 1 over q of x. And which would be minus expectation over p of the logarithm of q of x. And so fundamentally, what this is telling you is, again, a measure of difference between a distribution p and the distribution of q. And when you're looking at this equation here, it seems like, oh, we're only describing q. But keep in mind, we're taking the expectation over the distribution of p. And so these two things are different. And when it comes now to the minimization of the cross entropy, it's essentially the same thing as just sorry, let me back up here. What are we normally doing in a neural network or in a machine learning algorithm generally? Right? We have an empirical distribution, which is just all these raw data that we are feeding into the machine learning algorithm, and we have a model. Now, let's call one of them P, let's call the other of them Q. And we want to make the two of them fit as closely as possible. So we have that model with all these parameters, and so it's somehow conditioned on the parameter vector theta, and we want to make sure that the output of that model agrees with that empirical distribution that we have as much as possible. That essentially means that we want to optimize the mutual information between them, but keep in mind that we cannot influence the empirical distribution. Right? That is just something that's given. That's all the cats and dog pictures from the internet, if that is your input for graphic or for image classification or whatever other quantity you have. And so I really, when I'm just trying to minimize the distance between two distributions, I don't need to worry about the terms that depend only on the original distribution or the marginal distribution of the thing I cannot change. So because of that, whether I would now optimize my cross entropy, or optimize my mutual information, or optimize the Kullback-Leibler divergence between these distributions, essentially makes no difference. And the goal is always to optimize one of these quantities. I personally find it most intuitive to think in terms of a mutual information, and I want to maximize what I learn from my model, or or how closely I can approximate my empirical distribution with my model by maximizing the mutual information. However, in the machine learning literature, it's common to just talk about the cross entropy, and that's why you normally find the loss function that you encounter in the for the optimization or for the training process of your supervised learning algorithm, for example, as being the cross entropy between your empirical distribution and your model-based distribution. The connections actually go even further, and for example, the cross entropy also forms the basis of just the log regression problem that you're encountering. And even for linear regression, you can actually find out that if you're working with the KL distance or cross entropy or something like that, when you're dealing with the gradients that you need in the linear for the linear regression, you can actually also use gradients of cross entropies in order to find your optimum. And since we're here talking about the logarithms of ratios of random variables, right, you can also immediately see the connection to the log likelihood function that we were discussing 1 or 2 lectures ago in the context of the hypothesis tests. So, and of course, you can consider a classification problem in machine learning, again, as a hypothesis test. You're basically just saying, well, my different hypotheses are the different classes that I want to have as an output. What gives me the best log likelihood ratio? And that's the optimum solution for my hypothesis test problem. But that's nothing but saying that, well, I've got a classification problem in which I'm now using my cross entropy in some form in order to optimize my log likelihood functions. And so these are things, as I said, that seem to come from completely different areas, but they're all connected together here at the core, because everything is about the question, how much does a realization of random variable x tell me about random variable y? Okay, now moving to a still related but somewhat different problem, we are now coming to the core problem of digital communications. And that goes back to Shannon 1948, and who said that, well, what is the maximum amount of information I can get over a random channel, or over a noisy channel? And essentially saying that I have a source with a particular, I have a source, I have a destination, and let's start out with the simplest case of a binary symmetric channel. And we've dealt with that already quite a while ago. And we have a probability of p that I send out a 1, and it derives as a 0. And of course 1 minus p that it derives as a 1. And so there is a certain amount of error occurring on the channel. And Shannon showed that with appropriate coding, or with perfect coding, we can actually have error-free transmission. And at that time, that was an absolute breakthrough, because in the days of analog modulation, everybody was thinking that, well, noise is noise and there's nothing you can do about it. You're always going to have errors, but no, you actually can transmit error-free. So the question now is, if we have a certain amount of errors, what's the maximum rate at which I can transmit over that channel? And that is known as the channel capacity. It's defined as the maximum of the mutual information between what I have at the transmitter and what I have at the receiver, and the maximization occurs over the so-called input alphabet, or in other words, the probability distribution of the random probability mass function of x. And this here is the simplest possible problem of determining channel capacity, and people have been looking at more and more complicated configurations of channels with interferers and with relays and all sort of stuff over the past 80 years. If you look at the transactional information theory, you still have a section called Shannon theory where people are deriving capacities. But just for the to show you the fundamental principle and of how you would do this, you can say, well, what is the mutual information between x and y? Well, it's the entropy of y minus the entropy of y conditional on x, which is h of y minus the sum over our input alphabet, p of x, h of y conditional x equal x, is h of y minus the sum over x, this is minus p log p, minus 1 minus p times log of 1 minus p. And we're simply, sorry, this is p of x. Right? So this is the conditional entropy. This is where we're saying that, well, if we're sending out a 1, then what is my entropy of y? What is the amount of surprise? And then that is ruled by what is the p, because that's what I get if I have a 0, or the amount of surprise when I'm getting a 1 is ruled by the 1 minus p. So if I'm now just abbreviating this as h of p, small p, and this is not derived in any way that we're saying, oh, there is some secret formula for the entropy of channels, and we actually wrote this down explicitly from here to here, whereas calling this h of p is just a definition, and to avoid any misunderstandings. And so, but now I can write this as h of y minus h of p. And since y is a binary variable, of course the entropy of a binary variable can never be larger than 1. Right? I can never require more than 1 bit to represent the surprise in a binary variable. And that is 1 minus h of p. And it turns out that the uniform P of x maximizes this I, because you can write your P of Py of 0 is, of course, Px of 0 times Px, sorry, Py conditioned on x, your condition of 0 plus Px of 1 times Py of x, 1 condition 0 is 1/2 times 1 minus P, plus 1/2 P is 1/2. Right? So now you have y being a Bernoulli variable of 1/2. And we derive this mathematically exactly, but you can have a much easier interpretation of this fact here. Right? If you have a uniform, if you have a uniform input distribution of the x, then you also have a uniform probability of the y, because the probability that the 1 flips to a 0 is the same as the probability that the 0 flips to a 1, and so therefore we can say that the h of 1/2 is 1 bit. So h p of 1/2 is 1. H of 1/2 is 1 bit, and therefore our capacity is 1 minus h of p bits. Right? So this optimization of the input alphabet is something very important when we're doing our transmission. So you definitely increase your capacity if you are properly designing your input alphabet. And if you have a source that gives you with 99.9% probability ones and the rest as zeros, then you probably should be thinking about some type of source coding that makes it also better suited for transmission over a channel. Now, the binary symmetric channel is, first of all, useful as a toy example that you find out what is actually happening. But you could also say that, well, if I'm doing transmission over a noisy channel, for example, additive white Gaussian noise, right, and then I make a hard decision for every bit of whether I got a 1 or a 0, then de facto, at the output of my detector, if I just look at the output of this detector, hard detector, I find that, well, that's a binary channel. I just send out 1s and 0s. I receive after my detector 1s and 0s. So in that sense, you can say that's a practical channel. However, making that hard decision and only working with the bits that are coming out is not a good thing if you actually know more about the statistics of the errors that are occurring on your channel. Right? And the standard channel that we are encountering, not just in wireless, but in, for example, landlines, cables, and so on, is the additive white Gaussian channel. That is, I've got my yi being xi plus zi, so for every symbol that I'm transmitting, I've got my bits plus a complex Gaussian, a zero mean Gaussian noise. If you're doing bandpass transmission, then you would actually get the complex, but let's not talk about that here. Right? And you have a constraint on your transmit power. Your average transmit power, which just says your expectation over your x square, should be a p bar. Right? This is your power constraint. You're not saying anything about the instantaneous power that you're sending out in any particular bit or any particular symbol. You're just saying, on average, I don't want to spend more than p bar as my transmit power. And it turns out that the capacity, in this case here, is 1/2 times log 2 of 1 plus p bar over sigma square. And if you take into account that you have a particular bandwidth available for your signaling, it actually turns out you have w times log 2 of 1 plus p bar divided by n0 times w. So w being the bandwidth, and n0 over 2 being the noise spectral density. So, first of all, it turns out that the optimum modulation alphabet in an AWGN channel, so in a Gaussian channel, is itself Gaussian. So this is very different from the BPSK or from these binary modulation formats that we are normally dealing with. Right? We're saying we send a 1 or we send a 0, which basically is amplitude. Either we send, in terms of energy transmission, we send 1 or we send nothing, or we send something with a positive amplitude and an equally large negative amplitude. Right? So the PDF that we would be encountering there for the amplitudes is 2 delta pulses essentially, right? Because it's a discrete PMF. On the other hand, the information theory tells us that our PDF should be looking like this. Sorry, this should be symmetric. So this is very far from it. And when you're looking at early transmission systems, again, it doesn't matter whether it's wireless or any of the other ones, you see this very strong mismatch. When you do the analysis, you also see that these early systems were very, very far away from channel capacity, which partly was due to their coding, but it partly was due to the fact that the alphabet was so mismatched. Now, fast forward to 2025, right? If we're dealing with a 5G wireless system, you might have a so-called 256 QAM modulation in here, but essentially it just means that you have a much larger number of amplitude levels. It's also complex, so it's a little bit oversimplified what I'm showing here, but it's something that at least to a certain degree approximates a continuous distribution. It's still not really Gaussian, but it's certainly closer to the optimum than what we have with just these 2 delta pulses at 1 and -1. Right? So these are changes where information theory certainly has influenced things. One other interesting factoid is how much energy do I actually need for the transmission over the channel? And this capacity, or the capacity equation in this particular form, tells you, I mean, first of all, in wireless communications and in most others, you try to be spectrally efficient. Right? If you have a large bandwidth available, you want to use that for achieving a very high data rate. And so again, if you have laid a fiber or a cable at the cost of millions of dollars for digging up the street, you bought a wireless spectrum for a couple of $1 billion, right? You want to squeeze as many bits over the air as you possibly can. But let's say you're more concerned about energy than you're concerned about bandwidth. Let's say you have a deep space probe and you want to transmit bits with as little energy consumption as possible because you rely on a solar panel that's somewhere at Jupiter or farther out. And so could you just reduce your energy consumption by exploiting more bandwidth? And the answer is yes, you can, but only to a limiting degree. If you let W go to infinity in this particular equation here, and so if you let W go to infinity, then you have a capacity of P bar over N0 times the log 2 of E. And that is about minus 1.6 dB, and that is the so-called EPNO. And this is the energy per bit that you need to transmit, and the N0 is the noise power spectral density of your noise, which is just given by the temperature of the antenna and of your system with which you're operating. And so this is a fundamental limit beyond which you cannot go. Okay, with that we are done with the topic of entropy and mutual information. I want to use the opportunity also to do a little bit of advertising for the wireless communication course that is in the spring at EE 535. It's not really going to be focusing a lot on the information theoretical limits and so on, but it's going to be much more about the practical transmission systems that we have nowadays in wireless. And of course, there is a significant focus on the basics of it. How does a wireless channel look like? What are the basic modulation formats? What are the optimum demodulation methods? Very importantly these days, multiple antenna systems, MIMO systems. You might have heard the context, right? And then ultimately, how does it all come together in a 5G wireless system? There is, one of the reasons why I mentioned is that there is, of course, a connection to probability. It shows up almost everywhere. Right? When we're transmitting bits, we have noise on top of that. When we're building our decoders, we have to say, well, we know what we get is a bit plus an additive white Gaussian noise on top of it. The channels themselves are usually modeled as random, so they are characterized by the amplitude or power distributions that you actually get at the receiver, and so on and so forth. But as I said, the emphasis for that is really more in terms of how do the actual systems work, what are the physics of it, and the probability there is more of a tool that we will use, mostly just some of the results that we have in this course here, in order to solve the problems that we have there. And even for those, I think, who are mostly interested in machine learning, I think it's a good additional basis, because the future of machine learning is really in the application to different areas. And I mean, I know large language models are all the rage right now, but there is whether it's a bubble or not, there's debate about it, but in any case, there are a lot of different uses of machine learning, and most of them are in connection of applying machine learning to existing systems, like wireless. Right? You might have heard about the deal between NVIDIA and Nokia and so on. And in order to make this work, you need both the knowledge of wireless and of machine learning. And you cannot take machine learning as a black box, put it somewhere in a receiver and say, now let it work. You need to understand how the underlying systems work. So again, whether you decide to take a wireless course or not is, of course, will be completely up to you. But on a general note, I would recommend that you make sure that you have a sort of, if you focus on machine learning, that you have a second leg to stand on, which is an understanding of at least one underlying system to which you can actually apply those various techniques. Okay, this is a good time to take our break. Actually, we're already pretty behind on that, so let's resume at 9:25 with random processes. Thanks. Yeah, so we're starting with the last big chapter of this course, which is random processes. And just for those of you who want to follow along in a book, most of this is taken from, or accompanying literature, I would say, is Ross, and one of the books that's in the syllabus. And I think I mentioned it last time. It's a rather selective part that I'm presenting here. So the one challenge, if you want to read more about it in detail, is that reading Ross really is drinking from the fire hose. I think there are more than 300 pages about random processes. So unfortunately, I can't even tell you exactly, oh, we're doing this section and that section. It's very much eclectically collected together. So you would essentially have to look and see which of the parts you want to read in more detail or not. Or you can just rely on the notes that I'm writing down here. There is also some description in Gugner, and so that can give you a decent first introduction to the topic. And of course, you have some, maybe the exercises that you have in Gugner are a better practice for you than the little bit more advanced stuff that you find in Ross. Okay, that all being said, what do we mean by random processes? Well, let's just start out with the formal definition. A random process, or I'm just going to write this RP now, is a family of random variables, which can be finite or infinite, and in the latter case, it can be countable or uncountably infinite. And the basis for the family is often time, but can also be, for example, space. Okay, this all sounds terribly abstract. Let's bring in a concrete example of what we mean by that. So actually, also historically speaking, the first example of a random process was Brownian motion. And that was just Mr. Brown was observing particles in a suspension and was tracking their path through the vessel in which they were. And then it just started out here, and then it went something on a crazy trajectory like this. And so when we are now describing this as a function of time, right? Here, of course, time is a continuum, which would mean that our family of variables, that family is uncountable infinite because it's just the real axis of time. And we are not going to deal a lot with that continuous time random processes. Mostly what we're going to do is discrete time. And so let me now abstract this Brownian motion into something that is a little bit more time discrete. Right? And so now this would just be going like this. And so now we can say that, well, we have discrete time steps. At each time step, the direction of that particle is changed into something random, and now it's going into a different direction. And so you can say that, well, at each time step, I have a random variable, which is the new direction. Right? I'm picking one realization out of that random variable, and this essentially now is one member of that family. And the sequence of those members of that family is what we're calling the random process. So again, making this a little bit more formal, we can now say discrete time random process is family of RVs xn, where n ranges over a specified subset of integers. So now we're in the countable regime, and actually if we're allowing all times from 0 to infinity or from minus infinity to infinity, then of course we have countable infinity. If we are looking at an overall finite time interval, then we have a finite set. And so for a fixed n, xn of omega element of our sample space omega is an RV. And that's just what I was saying here with this discrete random walk. Every time instant, the new direction that we're picking is a random variable. Could be uniform between 0 and 360 degree. And for a fixed omega, we get a sequence of numbers x1 of omega, x2 of omega, which we're calling the sample path. And so what I drew here is one sample path, because it just takes on one particular realization of that random variable at each time instant. If I rerun that experiment, I'm going to get something probably quite different. And if I do it a third time, I get yet another sample path, and so on. Now later on, we're going to see a big question about random processes is of how much does the past actually influence what is happening at a particular time instant n. And in a number of situations, we have our random variables at the different time instances to be IID. And so we basically say nothing depends on the past. And that, of course, is a somewhat simpler case. There's still a lot of interesting characteristics that we can extract from that, and we're going to do a lot of them. But it becomes more complicated once we actually take the history of things into account. Now, imagine somebody driving through Manhattan. And you know the typical Manhattan grid. And you can basically say, well, at any cross-section, we are going to make the decision of go forward, go left, go right, with a particular probability density function. Right? And then you say, well, if I truly have a IID process in my evolution, then I say, well, I go here, maybe I choose I go forward, now I choose I go right, now I choose I go forward, right again, left, and so on. And then you can see that in this picture, we very soon come to essentially nonsensical paths. And you have a finite probability of just going like this. And that's typically not what you would be doing. So clearly there is the history of what happened before is going to influence where you're going to go. And there are other situations, like in the original Brownian motion, where there is no impact of the history because it's just the accident of the collision with another particle of which direction you're going to go, and so there an ID process is completely justified. So need to verify whether history plays a role. And one particularly important example is the Markov processes, which say that you only depend on one time step, but no longer history into the past. But we'll discuss that a little bit later on. But this is one of the most frequently used assumptions. Now, to give you a couple of examples for IID processes, and if you send bits over an IID channel, so you're sending bits over a binary channel with independent bit flips with probability p. Then you have xn being a Bernoulli variable with a parameter p. and xn n equal 1, 2, and so on is an IID Bernoulli sequence or process. And then you have your different sample paths, which could look something like this. And another sample path would be like this. And so on. Right? And so just to graphically also describe it, right, you would say this is sample path 1, 2, and so on. And then if you, so this is n, if you now look at this, you now see different realizations of that random variable xn, which of course has a probability density function that's Bernoulli with that parameter p. So xn can be continuous or discrete RVs. And now that continuous and discrete refers to their amplitude distribution. Right? We are now focusing on time discrete, right? So we're looking only at particular samples. But for a particular sample, right, we can still have a continuous probability density function of the realizations. So one example would be sampled noise, which by definition is continuous. And discrete would be, for example, bits, because there we know they are 1 or 0. Now, just to avoid any misunderstandings, the xn need not be IID over time, of course. First of all, so IID, as you know, means identically distributed. So do we have the same probability density function at every sample time for these bits? And that is not required. And so we can, for example, have an xn being the sine of 2 pi fn plus zn. Right? And now that zn could be, for example, an IID noise. But because we're adding this now to a time variant deterministic function, that means that the mean of this distribution of xn is changing with time. We can also have correlated processes. So for example, we can have a yn being 1/2 yn minus 1 plus zn. And so obviously whatever happens at time 2, 3, 4, and so on is still influenced what realization we had at time instant 1. And again, such correlation obviously make all the computations a little bit more complicated, but it's certainly something that is possible. Now, with excursion to continuous time random processes, we're typically describing this as a process xt for t. So it's characterized by the random variables xt. That's our family, right? And then the description of what is the range over which we define this process. And so this could be just time larger than 0, or it could be t between 0 and capital T for a finite time interval, or pretty much whatever we want to define. So what are examples for continuous time random processes? So first of all, we can have continuous noise. Any physical noise, additive White Gaussian noise, is by its very nature continuous time. Up here, we were just dealing with it as in its sampled form. If we have an ADC that only looks at certain discrete time intervals, right? But the physical process is continuous time, and that noise can be either white or colored. And so the noise spectrum can either be flat over frequency, or it can have a particular shape. And of course, the moment that we send anything through a filter, the spectrum is not going to be white anymore. We can have a carrier with a random phase. And I'm going to now make an important distinction. This is where we have a random process, and the randomness lies in essentially the start phase theta that we have here. Right? And so we can, for example, say, well, our theta is a uniform distribution between minus pi and pi. So when we're now looking at our different sample paths, and each sample path is a pure sinusoid. It's starting with a different initial phase, right? But once we've started, it's a pure sinusoid. There are no distortions on it. And that can happen, for example, if you have a really, really clean generation of a sinusoid, and then you just start to measure at some arbitrary time, right? You're not synchronizing anything. You're just starting to measure at some arbitrary random point in time. Now, a big difference to that is a carrier with phase noise, because there you have x of t being the cosine of 2 pi ft plus theta t of t. Right? So here, the theta itself is a random process. And so anybody of you ever built a little bit of hardware, no matter whether you're ham radio operators or built your own stereo or whatever, right? When you are using a local oscillator, then it's nominally oscillating at a particular frequency, but in reality there is always noise on top of that. And if you have an LC oscillator, then the noise is terrible. If you have a quartz, it's somewhat better. If you have an atomic clock oscillator, then it's pretty clean. But there's always some noise on top of it. And that noise is that phase noise that we have in here. So, and then that enters, of course, our equation for the output signal of that oscillator. So each sample path that we're encountering now here is not a clean sinusoid. And it's actually something that has a noisy process as its input. And so I'm just drawing these two cases. And in the first case I have, let's say this happens to be my sinusoid, and this happens to be another realization of it. Whereas in the other case, I'm probably going to get a sinusoid that in the extreme case might be looking something like this, right? This would be a sample path for the phase noise. And any time-changing phase is translated into a change in instantaneous frequency. So the instantaneous frequency we see here for that sinusoid would be constantly varying, depending on the random phase we're getting in. Okay, with that, we are at the end of the lecture today. We will continue with random processes on Thursday. Thank you.